I want to make this presentation because, as you know, attentional is one of the most important techniques used in deep learning. And basically, when we talk about attention, we always have in mind natural language processing and multi-head attention and RNN and so on. But actually, attention was also started with computer vision using pure convolutional neural network. And this is what I would like to emphasize on it today. So I'm going to provide the state of the art and the original work that were done around attention in computer vision using convolutional neural network. Okay, so the objective of today is to understand what are the attention modules in computer vision in CNN, and also get familiar with building an attention module using convolutional neural network. Okay, so first of all, why do we care about attention? Okay, let's take this example. So imagine that you have visited this place here in the mountains, very beautiful, and you would like to explore. Okay, so if you don't pay attention, what could happen? You will fall. So maybe you say, I would like to go here at the top, taking some pictures. But if you don't pay attention, it could be something dangerous. You can have a cheetah here. Okay, so even as a human being, we need to make some effort when we have these kind of situations in order to focus more to see if there are some kind of hidden objects that we need to identify. Okay, now let's try to make an exercise about attention. Is there any danger here? Is it safe to go? Will you go?
There is another cheetah, it seems like.
Yeah, somewhere. Okay, so if we make more attention, we're going to find another cheetah over here. So attention, you need actually to focus a little bit more on the features, on special features that you will find into an image. And this is basically the role of attention in deep learning. But of course, the question is how we can do that. And this is what I try to explain. How can we focus in particular features into an image using convolutional neural network? Now I think you've done enough exercise. You will be able to identify the danger a little bit more easier, right? Okay, so there is also another here. So basically, this kind of backgrounds mixed with the object, it makes it difficult for classical neural network to detect particular object. And this can be generalized to different other situations. Like for example, now we are working on aerial image detection. Usually we deal with very small object into very complex background and environments. And this is where we need to also pay attention to special features in order to detect, for example, vehicles, pedestrians, especially things that are very difficult to see without advanced approaches. Okay, so why do we need attention? It's actually basically to learn important feature faster. Okay, it's like we are mimicking human being behavior. Now, if you want, when I gave you the other images, you try to do some more effort in order to try to identify special features, and you have been a little bit more focused. And important information will be like the object or the target class that you want to localize and classify. So let me first introduce the different attention types. And before doing so, okay, there are convention in machine learning where we say soft and hard. Okay, so soft in machine learning, it means that we deal with differentiable functions. Okay, soft attention, because later on I'm going to talk about soft attention and hard attention. We need to understand this in a more general context in machine learning. When we say soft, it means that we deal with differentiable function, like for example, sigmoid or softmax, as you can see here in the plot, they are differentiable. And since they are differentiable and they are continuous functions, so we can use gradient descent. So this is why we use gradient descent in backpropagation with this kind of nonlinear function. However, in hard machine learning models, the functions are usually non-differentiable, like for example, the heavy side step function, as you can see. So the derivative here is 0 in all points except at the origin, okay, which is an impulse function because it's discontinuity. You don't have a continuous function. And in these kind of situations, so in soft machine learning, we use usually gradient descent, whereas with hard machine learning models, we use reinforcement learning in order to train the model. And okay, based on this definition, we have hard attention and soft attention. So they apply basically the same concept. Okay, so hard attention, it uses reinforcement learning to focus on specific parts of the image, and it deals with non-differentiable functions. And soft attention, it uses learning weight. Okay, it uses gradient descent in backpropagation with differential and continuous function. And this is pretty much used in many computer vision fields like classification, detection, segmentation, and video processing. So now we are going to focus on soft attention. We know the different categories, and let's see the categories of the soft attention. We have basically it's channel attention, spatial attention, or both together, hybrid models. Self-attention, we're not going to consider today, we'll see this in future lectures. So I'm going to explain channel attention and spatial attention, and the concept is very simple. So usually when you do, for example, any pooling or any operational matrix, you're going to choose a particular axis. And you know in a feature map, you have usually several channels, okay, and every channel will represent one feature map, which is almost like an image. Okay, so channel attention, it means you are going to exploit the inter-channel relationship of the features. You are going to extract information at channel basis, not spatial basis. Because an image, okay, if you take an image, one image, this is a spatial distribution of the pixels, right? And from one channel to another, you have another image. Okay, so basically you can do an operation over the channel axis or the spatial axis, and based on this, you will have channel attention or spatial attention. Maybe it's a little bit abstract, but I'm going to show you through examples how this is going to happen. So channel attention is focused on what is meaningful given an input image. Okay, and spatial attention, it focuses where an information is located. Okay, so this is more with finding the position of the feature. And this one will try to identify the particular features that we want to find. And mixed attention, of course, it uses both channel and spatial. We are going to see some of the state-of-the-art models that uses a mixture. And most of the state-of-the-art models, they use a mixture of both. They make a channel attention, spatial attention in parallel, then they combine both together to generate a feature map. Now I'm going to provide 3 seminal works in chronological order. The first one is Squeeze and Excitation, which is pretty much known as the SENet architecture. It was proposed in 2017 and published in CVPR 2018, and you can find it on ArchiveX. And let's see how they have managed to implement attention here. So the Squeeze and Excitation block, as you can see, it is designed to improve the representational power of a network, and it uses a dynamic channel-wise feature recalibration. So the idea here, basically, you have a feature map like this. You are going to make some kind of squeezing or compressing the information over channels or over space to generate some kind of extra weights, or we can call them masks, and you will multiply these masks by the original feature map in order to emphasize more some particular information that you want to focus on. So you can consider this at a very, very abstract level. We're going to generate a kind of mask with some spatial weights or some spatial probabilities. And later on, we are going to combine these weights with these weights in order to emphasize some of the specific features. So you say how? And this is what we are going to explain. And by the way, this algorithm was the winner in ImageNet competition and has helped to improve the result 25% more than the previous year. So let's look at the idea here. The idea is to add parameters of a convolutional block so that the network can adaptively adjust the weighting of each map. So here it's based on feature recalibration. How do they do the feature calibration? They are going to use a global average pooling here. And this is going to transform this feature map into one-dimensional vector. So this one-dimensional vector is going to, I'm going to explain the global average pooling to understand what's going here. So here you will have some special weights that will be extracted from this feature map. Then they apply two dense networks, okay, with some weight for non-linearity to generate this kind of mask that later on will be multiplied by the feature map. So this one will in fact, because if you have C channel, okay, and C inside the network, it can be more than 3. We start by 3 channels in RGB, and then you can have more channels. For example, here 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 channels. Each channel will be multiplied by a particular weight here to emphasize. And so why it's called squeeze and excitation? So this operation is squeezing, okay, because it's going to compress the whole information into one-dimensional vector. And this part here is excitation because it will be applied to a dense network. So there is an activation function, ReLU and sigmoid function that you're going to, this is what you call excitation. So when we have activation functions. Okay, and finally you are going to generate a feature map, another feature map that will emphasize more the features that we want to focus on. Of course, over many iterations is going to converge to more information. You'll see this later on. So let me explain the global average pooling, because global average pooling, it's a bit different from the average pooling that we know. So given an image like this here, so let's say RGB image, global average pooling is going to reduce the size, and basically every pooling, the objective is size reduction, okay, to extract only important information. Okay, so all this image here is going to be, for example, the average will be 5. Okay, and then we take this image and the average will be 3, and this image, the average will be 1. So we go from, for example, here 3 by 4 matrix to only 3 by 1 matrix. So this is our number of channels. Okay, and all the special features, now if you consider these channels and this is special, all the special features are going to be reduced to only one number. And this one number is going to represent like the average of all the numbers over here. So you can think about this is kind of digest. But of course, this digest is going to be later on multiplied by the original feature map in order to provide a little bit more information. So the output from the global average pooling is always one-dimensional tensor size. So what's the role of, when do we need to use the global average pooling? You know, usually when you have a convolution neural network, at the end, you need to make flattening to have only one-dimensional vector before going into the dense layer for classification. So one of the ways to replace flattening is to use global average pooling. Okay, so you can replace your fully connected blocks by an average pooling on the last layer feature, so to have only one-dimensional vector. That's one of the possible ways. Okay, and here the idea is to generate a feature map for each corresponding category of the classification task in the last multi-layer perceptual convolution layer instead of having a flattening operation. Now coming back to the squeeze and excitation block to understand it again. So we have an original feature map here. We're going to apply a global average pooling. So now I think you understand because we have only one number. Okay. So this number is going to go, look, the algorithm is very simple. Global average pooling, one dense layer and another dense layer. And here there is the rule is the first dense layer after any pooling is going to have dimensionality reduction. So if you have the number of channels, you will divide it by a certain ratio. And this ratio sometimes is calculated empirically, which ratio will provide the best performance for you. Okay, I'm going to show you some of the results based on this. So here is going to apply first dense layer with lower lower number of nodes with an activation ReLU, and at the end it will have the number of channels, and they will use sigmoid activation. Finally, after we generate this mask, we multiply. So here it's multiplication, these numbers by the feature map Spatial, and we're going to have this one. So of course, this has made an improvement, as already mentioned, in ImageNet competition by 25%. Okay, so If we go to the steps, global average pulling, then first fully connected layer with ReLU function, second fully connected layer with sigmoid, okay, to give probability for the features, and finally multiplication of for weighting the feature map. And this is the Is it clear for these steps? Is there any question? Okay. So the basic idea, as already mentioned, is like to create a digest, either over channels or either space. Here it's only channel-based attention, by the way. You don't have a spatial attention, okay? Because you made the average pulling based on the channels. We have compressed all the weights. In 2018, these authors, Park and Paul from Korea, they have made another model that is called Bottleneck attention module. So when we say bottleneck, what does this remind you? Which architecture, which classification architecture? ResNet. So ResNet, it has bottleneck modules, okay, that are stacked one over the other, which we call them also residual blocks, okay. And so this was applied to ResNet, by the way, and it's another technique to apply attention. And here they use spatial attention and channel attention. So this is kind of mixed attention model. And the objective was to efficiently improve the representational capacity of the network. And here it uses a very nice concept that is called it's convolution. Convolution, you have a kernel 3 by 3, and you will make it, okay, you'll multiply it by 3 by 3 pixels over the feature map. And you can add stride and other parameters. So dilated convolution, I'm going to explain, is going to make space between the pixels when to apply the convolution. We'll talk about it. And it builds a bottleneck structure as suggested by ResNet. It was applied in ResNet to save computational cost. And this model uses both channel and spatial attention in parallel. So here we have channel attention, and here we have spatial attention. And you can see in very simple manner, we're going to calculate a channel attention map, a spatial attention map. They will be summed together. They apply sigmoid for non-linearity. They will create a global attention map, and then this global attention map will be multiplied by the original one. Okay, so it's basically the same concept. This is the same concept applied to. I have a slide, but I put it on. I didn't put it in the right order. I'm going to show it to you. It gives you an abstract architecture for these kind of models. So basically, you can define your own channel attention, your own spatial attention. You just need to multiply them, add any non-linearity here, generate something that combines both, and then weighted with the original feature map. And this is going to give you more information. So what's the idea here? Why do we think this is going to create attention? Why this is going to lead to an attention?
To focus more on the spatial.
Yeah, how the focusing is actually being made. That's the question. Because, okay, what tell me that is going to create an attention? At the end, it's matrix multiplication. Is there any logic here?
Because during the learning, we learn the best weighting for every channel or every spatial feature. So the learning will focus more on which channel to prioritize, or which pixel to prioritize.
Yes. Well, if I try to go to the general model. Okay, I'm going to stop here, and then we'll try to find the general model. Because if we understand the general model, that is going to be easier to understand the rest of the model. So this is the model. Okay. This is the base attention structure using convolutional network. We have an input feature map. Okay, consider this as a black box. And you have a refined input feature map. And so how do we create this one? We're going to have an attention module. And basically, it will be kind of convolution block or average pulling block with some multi-layer perceptron, okay, dense layers, and non-linearity through sigmoid. So this is basically this. Now it's up to you to decide what you put is as convolution, what to put is as average, how to stack them. This is where you can play with the architecture. Okay, but basically all you need to do is to generate a 2D or 3D activation map, which will act as a weighting module for your original feature map. If you understand only this from the presentation, you get through the whole attention picture for computer vision. Okay.
Basically, this activation map.
Yes.
Is doing the same thing, channel and spatial.
Yes, you can do it. If you are going to squeeze with respect to the channel axis, you're going to have a channel attention. If you are going to squeeze with respect to the spatial axis,
optional 2D, 3D.
Yes.
You want to spatial 2D,
yes.
3D with channel.
You can generate 2D. You can generate 1D vector like in SqueezeNet.
And the channel.
Yes. It's up to you to decide how you want to generate this activation. Okay. And all the game is hidden. And basically, what we need to do is actually to try to add some additional weights on this original feature map to see whether there is something really important. So now I come to my original question, why this lead to an attention? So basically, when you squeeze whether over the channel axis or over the spatial axis, you are going to create like a digest of the information over there. And this digest will be represented as kind of weights.
And most likely,
yes.
The 2D, 3D maps, you can see a lot of zeros. You have a lot of zeros.
Here?
Yeah. That's the only way to squeeze. Then let me find a lot of zeros. Imagine you're going to have a lot of pixels coming from an input feature map. It's 0.
Yes, here it's going to try to zero the background and emphasize more the feature, yes.
Yeah.
And you can do this over the channel because every channel will carry particular information. You can find some edges into one channel, but not in the other. And over the space, so the space, it contains object and background. And in this case, you can try to differentiate. So the attention module at the end, when there is no differences in the pixels, it try to make it zero as a zero mask. So later on, and I will see you later on, what's the output of the feature map, you will get more the idea about what I'm talking about. So global average pooling or convolutional, especially one-by-one convolution, which is introduced by SENet at some point in time for dimensionality reduction. And if we can understand this in a holistic manner, dimensionality reduction is usually, I don't want to care about many features, but I want to care about important features. Okay, and you can do this max pooling. You will emphasize the high intensity edges, for example. Average pooling, you want to understand what's going on in average into the feature map. So we need to have kind of sense. Usually when we started to learn about deep learning, we take this as from mathematical perspective. We are going to do dimensionality reduction, but we didn't try to explain why this is going, what this is going to give us. It's going to have features, but we don't know to which extent. Now I think the AI is more developing to an explainable AI. So you find more and more in recent papers that they try to explain the architecture that they're trying to design. Okay, and the explanation, this is at the end an interpretation, but it has some kind of logic. Okay, when we try to, for example, create a digest of a feature map, it will give us a little bit what's happening in a particular region of that feature map. So let me come back now to please finish this. Okay. So now we are applying the same principle. We have an input, we have an output, and we want to generate this one. Okay, this is the block that is going to generate. Of course, it has two blocks here, one for channel, one for spatial. So for channel, we're going to use average pooling as they did before. There are some people that use pooling, average pooling, max pooling, combination of both. We have seen many architectures. This is why I told you, you can play your game here. You can think about any architecture and just try to make it work. There are people that also for channel attention, they have parallel stream, one with average, one with max, and then they combine in some manner. But the principle is the same. And so here it's similar to the SE. This block is similar to the SENet because it's average fully connected with dimension D reduction. So what is the contribution here? They try to combine spatial. So instead of making the so here the convolution will be made on with dilatation of value D. So before going into the details, so let me remind you about the result bottleneck architecture. So this is what we call the residual block or bottleneck block. Is where we have 1 by 1 convolution, 3 by 3 convolution, and 1 by 1 convolution. They are stacked over the other, and this is where the attention was actually applied, as we will see at the end of this presentation. So dilated convolution. Let me show you this video. Okay, so here you have the normal convolution that you already know. This is dilated convolution. We will make a dilatation so between the pixels. So this is normal convolution when the rate is equal to 1. Okay, you're going to apply the kernel on the neighborhood pixels. So if you make a rate of 2, you're going to make a pixel in between. So the convolution will be made on these pixels.
And it pixel, but in between zeros or what? How zeros?
The kernel, instead of making the kernel making the weighted sum here, it will be making the weighted sum over these pixels.
Yeah, and can I assume because in between is 0?
Yes, it's not considered. I'm going to explain why. If you make rate equal to 3, okay, so we're going to make here. So this actually, what's the purpose of, this is what we call the dilatation rate. Dilatation rate, and they usually spaced inserted between the kernel element. It was developed by Princeton University in 2006. It's sometimes called Hypermaters convolution or whole algorithm.
This is Arthur algorithm.
Yeah, this is Arthur algorithm.
I learned it.
Yes.
This is exactly I learned it.
Yeah.
Exactly I learned it. مرة learned it.
Yes.
That's what he did. دخل zeros
Yeah.
That was 1988.
Yeah, and what's the purpose here? What is the purpose here? What's the advantage?
To get more receptive field from the image.
Yes.
Because convolution can only concentrate on smaller spatial feature.
Excellent answer. So here is going to make a better exploration of the space. Instead of focusing on narrow area, it will allow you to expand a larger area without having to change the resolution. Okay, so expansion of the receptive field without the loss of resolution. And so this is actually similar to pulling and strided convolution, but both they reduce the convolution here.
Yeah.
But dilated convolution has the advantage that it doesn't reduce the resolution.
That's expanding.
Yes. Yeah, and because here we said it's expansion of the reception field, so I would like to remind what is a receptive field. So receptive field, for example, like if you see here in the image, this is a receptive field and this one is a receptive field. So which one would you think will be the best? So having something very small receptive field has drawbacks, and very big receptive fields have also drawbacks. And this is why the dilatation rate, it's a hyperparameter that we need to tune. So you don't have it very big or very small. And this depends on the average size of your target object or the object that you would like to classify. This is the first information, okay? It's defined as the size of the region in the input that produces the feature. Okay, and this, of course, it's not the standard. It depends on your target object that you want to classify. Some objects are big, some objects are small. So if you are classifying aerial view images, it's not like you are classifying fixed camera images. There is a difference. Okay, so how to increase the receptive field in CNN? Techniques that you already know. You add more convolution layer, so you go deeper. Okay, you add more pooling layer or higher strides convolution, or use dilated convolution. Another way is also depth-wise convolution. These are the different techniques that are used in CNN to increase the receptive field. So when we want to design a new CNN architecture, we need to think very smartly how to combine all these different features in order to optimize the receptive field with respect to the object classification. And now maybe you are making one mistake. We take any classifier, any object detector, and try to plug it and make very few. We try to make more object or training algorithm, but we never think about how to optimize the hyperparameters to optimize the receptive field size, which will help a lot into improving the accuracy of the image.
Do we have to can we make use of multiple convolutions at the same time?
Yes, yeah, you can have multiple layers of convolution, of course, and every layer is going to extract some fine-grained features. If you go deeper, you are going to extract more and more fine-grained features.
Just like the BGG, 3, 5, 7, 9, 11.
Yes.
They go up to BGG.
Yes.
They have like 4. At each convolution, they have four different canons.
Yes, SENet, it can go up to 201 layer. Okay, so here let's look at so channel retention is pretty much similar to what we had before. It does global average fully. It will make a feature channel vector C by 1 by 1. C is the number of channels, and then it applies multi-layer persona, which is just two dense network with dimensionality reduction. So here it shows the output, but it doesn't show the architecture of the network. Here we have dense neural network with number of channel divided by R. So for example, if you have 1024 channel and the dimensionality reduction is 16, in this case you will have 1024 divided by 16. This is the number of neuron in this dense layer. Okay, and here you will have a complete channel number. And this is to reduce the computational cost. And finally, we generate a channel retention map. Okay, and the algorithm is pretty much simple. It's just global average pooling with some dense networks and put all together in stack.
So they apply this to every layer?
No, and that's a good point. They tried to apply to every layer, but it doesn't give. I will show you the results because I prepared present this paper. The spatial attention module, this is the novelty here. They use 1 by 1 convolution to reduce dimensionality with the C divided by R channels. 3 by 3 convolution, 2 times, but contain dilatation values. So here it will be for. This is for dimensionality reduction, space exploration with dilated convolution, and another 1 by 1 convolution to reduce the output channel dimensionality to 1 by H by W. Of course, here the use of 1 by 1 convolution, it's up to you how to make it. It depends on what will be the output that you want. If you want 1-dimensional vector, 2-dimensional vector, big, small, this is up to your design. Okay, I have seen many architectures that has different type of output dimensions. Okay, so there is no rule here. It depends on the output and how you want to combine it. Look now, this channel retention will be just undergo element-wise addition, and they are not of the same size, so they will be using broadcasting here. Okay, broadcasting to add these two elements, and you can see this is like a heuristic. Okay, and then they apply sigmoid, and they generate what we call the bounded tension map, which is that of these two. So using broadcasting on this, of course, you will have for each layer you have an attention. Okay, and will be replicated, and basically you will have the same. You will have the same dimension of this one, so you will do element-wise multiplication at the end, and they apply batch normalization. Here, it's not shown.
To the mask.
Yes, yes.
To the mask.
Can you change the position of the? Yeah, okay. Let me change this. Okay, so here you have multiplication, and then you multiply this by 1 to weighted, and then you take this one and you add element-wise. This is the same architecture that we presented before. Voila. Okay, and you can see the size of this one is different from what was generated by SENet previously. And it's open source, it's in PyTorch. Okay, the final step is to generate the map attention function, which is M channel plus and M spatial added together, applied sigmoid function, and then making multiplication and element-wise addition. The final step, the attention MF, will be multiplied with the input feature. Okay, we already talked about this. So now your question, Dr. Hawari, where to place the BAM? So they made many experiments which I'm going to show. Okay, they tried to put the BAM module inside every convolution layer, but at the end, they ended, the most optimized manner is to put it between the bottleneck layer, between the residual layers. Okay, and this will help actually to extract more features, and they made improvement. They made improvement as compared to the original ResNet. Okay, so this is how it looks like. You have an input. This is ResNet architecture. You have different residual blocks, and you will put the BAM. So every BAM is going to emphasize more the features under the classification. And of course, it can be applied to classification, object detection, object segmentation, because usually we use a classification backbone in any of these algorithms. So they made very nice analysis for their algorithm. So first of all, they started by hyperparameters impact. So what they have done, they have analyzed for different dilution values, starting by 1, 2, 4, and 6. And finally, they find 4, it gives the least error. 4, it gives the least error here. Because now what they wanted to do, they want to find what are the best hyperparameters. They will take it, they will compare with other algorithms. Okay. The reduction ratios, they have tried 4, 8, 16, 32. And they used 16 because it also gave the lowest value. And the base ResNet, it gives 21 or 41. They have also applied channel, spatial, and both together. And these are the results. So using the whole architecture, they found that they can get the least error for SENet 100. And here, experiment comparing the convolution. They have used different types of architecture. Yes, of CFAR 100. Yes, this is they wanted to extract what is the best hyperparameter, what is the best configuration, and then they also made experiment about bottleneck versus inside each CNN block, where to put the intention module. Okay, so here, as you can see, this is BAM at each convolutional layer, and this is BAM at each bottleneck. So they found, for example, look at each convolutional layer, you will have 80.88, 20.88, but it's only 24, only at the bottleneck. This is where to place
and the smaller size of parameters.
Yes.
Smaller size.
And of course, if you put in every layer, you will have more parameters and more flip-flops, so more computational cost. Okay, because here they care about the computational cost. So in all cases, in different type of networks, they found placing the attention module at the bottleneck of ResNet will lead to better results. Okay, so this is something that we need to care about. If you make any attention module, is where to place it. So we need to analyze this. We need to analyze the hyperparameters. We need to analyze the placement of the attention module. Okay, now they extended the experiments on CFARnet and ImageNet 1K, and they have made different types of classifications. So on CFARnet, it's basically the same result. They applied on DenseNet, ResNet, wide ResNet, pre-ResNet. Here you can find the results. They always find that the attention module consistently improves the result. And here they applied on ImageNet 1K and they compared top 1 and top 5 results. So it's consistently when there is a BAM attention module applied at the bottleneck, it always gives better results. So look, it's small improvement, but of course, considering the number of images, it will be huge. Yes, look from 1233 to 11.6, and the G-flops doesn't increase too much, I mean, it's only very small computation cost as extra. And the number of parameters is also reasonable in terms of increase. Comparison with SqueezeNet, so they compared because at that time it was state of the art. And of course here, the difference between SqueezeNet and BAM is that BAM introduces spatial attention in addition. And you can see comparison, this is ResNet, this is with SENet, and this is with BAM. So there is also improvement consistently on CIFAR-10 image classification. And if we see the comparison about, so SENet here, it consumes more parameters as compared to the, which I don't understand well because it has more convolution layers. The attention mechanism here, it has more convolution layer. But these were the results that were posted. The same authors have made another improvement, which is called convolutional block attention module. Okay, and it's available on this paper. So they use the same structure that you have already introduced. Okay, and usually we start by H by C feature map, and we generate an activation map. Of course, it can have different shapes, not only this one. And finally, we have the defined feature map. So the idea of CBAM is to use channel attention module and spatial attention module as well to generate a refined feature. So this is the overall architecture. So here they will make it in sequence, not in parallel. Okay, in the beginning they made it in parallel, and now they make it in sequence. They extract the channel attention features, and they will multiply element-wise to the feature map, and then they will take this output, apply it to a spatial attention, and then define feature map. And they did nice experiment to say, okay, why I don't put this one before and this one after? Okay. Okay, so the channel attention map, as already mentioned, it tried to attract what is meaningful in the input. So they apply max pooling and average pooling, not global here. They apply this, and then they apply to advanced layer. This is the channel attention module. And finally, they generate two feature maps. They will add element-wise, max and average. They apply the sigmoid, and this is our channel attention. Okay, so you can see now they made an improvement. Instead of using global average pooling, they used a combination of parallel max pooling and average pooling here. Okay, max pooling semantic. So what does it mean, max pooling? Usually, if you have a feature map like this, you apply max pooling, you're going to take the max at each of these elements. But what's the benefit behind it? So the max pooling operation calculates the maximum value and create a downsampled feature map. It adds a small amount of translation invariance, and it will extract pronounced features. And it will take the lighter features and remove the darkest ones. Okay, so the features here are more pronounced, like for example, edges. The average pooling, okay, same thing, and here it extracts more smooth feature than max pooling, and you can understand because when we make the average, it's going to be a little bit more small, but here it's going to take sharp features, and here the idea is to combine both together, trying to capture more features that probably they are hidden somewhere. So this kind of redundancy, it also improved the channel attention mechanisms as compared to the previous technique. So, and this is the kind of thing that you need to understand. For example, if you want to make an architecture making average pooling or max pooling, you need to understand what this is going to lead into your feature map at the end. So let's get started. So in the beginning, it will make an aggregate spatial information of a feature map by using both average pooling and max pooling operation. Of course, it will be aggregated with respect to the channel axis. Okay, so this is going to digest the whole spatial information into feature vectors. and then it will apply multi-layer perceptron, which is a dense network, and this is with dimensionality reduction. Okay, so first dense layer, second, this is the output will be combined into this one. We make a dense layer with the reduced number of neurons. We generate this one, then an upsampling with the larger number of neurons, and then we will create two feature vectors, will be added element-wise, and we'll formulate our channel attention C by one. So we will summarize all the spatial information, and we'll just keep the channel, only the channels. And the output feature vector are measured together, element-wise, and finally, it applies to sigmoid for non-linearity and generate the channel attention. Okay. So all this channel attention will later on be multiplied element-wise with the original feature map, which will be the refined output. And this refined output now it will undergo another special attention module. Okay, so the special attention module, it tries to explore the interspatial relationship and where the information is located. So we try to find where the feature is located. And here it uses average pooling and max pooling along the channel axis. Okay, so it's going to summarize a part of the feature into a smaller one. Okay, using both max pooling and average pooling. So this one is for max pooling and this one for average pooling, and it will generate this combined feature map. We apply the sigmoid, and this will be the special attention module. And this is the code over here. Then we apply convolutional layer on the concatenated pooled feature. So here we apply a convolution layer. So this is the convolution here. And then it will to generate special attention map, which encode where to emphasize or suppress. Suppress the background, emphasize on the object. Okay, and finally we generate the special attention map MS. So at the end, we have here, we create the refined total feature map. So this is 1D, this is two-dimensional. And this summarizes the whole convolution block attention module. Now, what are the results? First of all, they compare the different channel attention methods. Okay, so here they have used average pooling, which is only used in SE. SE used only average pooling. So here we evaluate only the attention module, not the total. And the attention module using max pooling and average pooling, it provided better than max pooling alone or average pooling alone. So here we can understand that combining different type of pooling or different type of methods, it can improve to make more attention to the object that we look for. Okay, you can see here, it makes a better reduction. And if we compare only average with max, so average give a little bit better information, less error than the max alone. But both combined, it give better error. Impact of the special attention alone. So here ResNet plus channel attention, ResNet plus channel. And here they use different types of kernel for the convolution. Kernel 3, kernel 7, kernel 3, kernel 7, with average and max, and here one-by-one convolution. They try to explore different type of dimensionality reduction, and they found out that channel plus spatial with the kernel equal to 7 and average and max pooling, it gave the best result. This is why that was their final architecture, with a kernel size equal to 7. Of course, this is not standard. Maybe if you change the data set, you need also to compute again these hyperparameters. This is combining and channel attention both together. Okay, so here when they put them in series, and here when they put them in parallel. Okay, so in series it gives less error than when the spatial attention was in parallel. Sequential channel first. Yeah, this one is spatial first, then channel. And this one channel plus spatial. So even the order, it can also impact. I'm not sure whether this is general, but maybe it's dataset dependent or object size dependent. But for this particular ImageNet 1K, this result helps. It's not moving. Okay, classification on mobile net. They have also tried on mobile net with CBAM. So it gives also less errors than mobile net plus SE or mobile net alone. So we can see in terms of parameters, there is an increase, almost the same with the SE. In terms of G-flop, it's very comparable. And in terms of top error, 1% or 5%, CBAM provides better performance. We have already seen all of this. See, I'm going backward. Yeah, this is the curve for training error, both on ResNet and MobileNet, for different type of different type of architecture here. So the convergence for MobileNet plus CBAM, it provided lowest error for the validation. And this is for the train.
بس الاكس اكسس ما هو كان سكيلينج.
This one?
Yeah, كم سيفهم كم
80 epochs, I think.
80 epochs.
Yeah, it's 80 epochs. Yeah, this is now what looks like when you apply attention. This is very, very illustrative. And here they use the Grad-CAM. I don't know if you have heard about this. This is a visualization tool that allows you to see the output feature map at every level that you want. So this is the input images. And here, when we apply ResNet on, so you can see the level of focus. So for example, here you want to focus on cat or on this type of objects. So when ResNet with SE, you can find here the result. And ResNet plus CBAM, so you can see the focus is more intense on the objects. And this is, what does it mean, attention? Okay, so the focus will be here, the focus will be here. Look, at ResNet alone, it only focuses on part of the image. And this will weaken the classification. Look at the probability here and look at the probability here. Okay, look at the probability here as well. So in all cases, the probability of classification is much higher when we apply the attention module. Okay, from 0.8, 0.96, 0.87, 0.11 here, 0.19. Here it's slow because it's confusing. You have two objects.
Yeah, but still, I think so many classes.
Yeah.
Because one is good.
Yes. Yeah. And yeah, we have 1K classes.
Yeah.
Yes. Here it's a very high classification. Look, from 65 part of the image. So we can see the impact of attention. Actually, it really helps to improve visualization. This is another example over here as well. Look, it perfectly goes around the object. And this feature map is this is what is going to help in classifying properly, okay, by putting more attention to the features that will impact the classification probability at the end. We apply this to object detection. And again, the MAP has increased in all cases. Okay, MAP at 0.5, 0.75, and between 0.5 and 0.95. This is for object detection MEP on VOC 2007 test set. Okay, it went up to 70%, 70.5%, and on mobile net, and 79.3 on BGG 60. And you can see here the number of parameters, there is no major change. Okay, so as a reference, you can look at the paper of code, by the way, it's an excellent reference. Yeah.
It's amazing.
It provides nice summaries. It gives you also all the different attention modules. You can have a look. Sometimes it's not very comprehensive, but at least it gives you the essential, it gives you the reference paper. And Medium as well, toward data science, they provide complementary information about these things. Okay, so I come to the end of the presentation, and thank you very much. So yeah, I think, you know, for me, I want to do this presentation. I want to share you all these thoughts, because I think it can open us a lot of horizons since we are working deeply on the image learning, on deep learning with computer vision, especially on small objects. We work a lot on aerial images. Our work in the previous was just trying to customize existing models without making any more contribution of them. So I think now we can change the backbone classification models, whatever we use, SENet or DenseNet, and we try to come up with new architectures that are justified, explainable, about attention module using convolutional neural network. Of course, I think this theme has to be expanded more, and I want that we make these seminars kind of regular routine in the lab. Everyone who learns something, and I learned something I want to share with you. If you learn anything, please share with us, because if we exchange information, I think we can improve much faster. Because if everyone, you know, in the beginning, I started to read these papers, I was a little bit confused. Everyone provides you the information with different terminologies, different syntax, then, okay, let me make a unified presentation with some orders. Now I think it becomes clear for me, and try to convey the same message for you. And I hope if you learn anything, you can call for a seminar like this. And I'm going to also to explore more other attention modules, because I think this is now the future for computer vision for convolutional neural network. You know, for me, I have personal concerns about transformers. Also, transformers are most known about using attention modules like multi-head attention and so on. The main concern is, like, I have a concern on blockchain, is computationally heavy, and also requires a lot of data, which is almost 99% of the cases is not there. So you apply it on ImageNet or this kind of huge database, it may work, but I'm not sure whether someone has trained on a small data set. Like, for example, I have asked the question for Sadaqat when he made about healthcare. I'm not sure whether there is a successful experience about transformers. So transformers is good from academic perspective to explore more, but if you want to make something academic and at the same time it can lead to some business-oriented values, for example, like improving all the different classification, detection algorithms that we have here, I think we need to focus more about attention using computer vision or anything similar techniques that may help us to improve our records. Yes. Thank you. I don't know if there is any question from online or, okay, let me see.